Welcome to Unit 1, Measurements. This is Mrs. Irwin, and I'm here to talk about scientific notation. We'll follow along with significant figures, and finally with conversions. So let's get started here. Welcome today. We are going to start with scientific notation. You know, if a number were really small or really big, it would be really hard to say all the zeros. So rather than get really tired through saying all those zeros, why not write it shorthand? So we have a system called scientific notation where we can actually show the value of the number without writing all the zeros. So for example, 2300, what you would do is you would look at the thousandths place and think of that as 10 to the third. So then you think, all right, 1,000 times what would be 2,300? So 1,000 times 2.3. You can see that the decimal is right behind the very first non-zero number, and this we call scientific notation. The next number, as you can see, would take forever to say all the zeros. So instead of saying that big number, we could just write 2, so the very first number on the, starting from the left, that's a non-zero. And then you could put the decimal right behind it. And we keep 4 digits because there are 4 digits that we actually count as being significant. I'll talk about that shortly. And the fact that the value is a decimal 13 spaces to the left of 1. That makes the power 10 to the negative 13. So it's a very small fraction of 1. Okay, significant figures. So when scientists have a tendency to collect values and measurements, they can't have it randomly collected, so they have to have a system. So we have this system that allows us to look at the values based on what instrument we collect them on. So let's see. So we have these significant figures rules, for example, and they really won't make sense until we actually apply it to some machines, but for now we'll just start with the rules. So if you have non-zero numbers, they're considered significant. So they are numbers that we rely on and count. Number 2, if you have zeros in between non-zeros, they're also numbers that are being measured. Number 3, if you have zeros at the end, at the far end, if you see them to the right, they're not significant unless there is a decimal place there, and as you can see, there is a decimal place here, so that's purposefully saying, hey, you know what, I am reading all of these numbers on a scale. Say there was a scale that weighed to the nearest tenth of a pound. Let's say we were weighing a cow. Okay. All right, number 4, zeros, if they're in the very, very left of the number, no matter where the zero is, or I'm sorry, no matter where the decimals are, those aren't being counted. They are just telling you how big or small, like the actual sort of degree of the value. However, when we're actually measuring values, we're measuring the 2, the 1 on to the right of it, and then the 0 to the right of the 1 in this last number. So this would be as if you were weighing perhaps a gnat. If you're weighing a gnat, which is really small, and you put it on a very small scale, you're only going to be measuring with accuracy here those last 3 digits. All right, time to test yourself. How are you doing? The first one, how many significant figures? Give yourself some time. I'll come back. right, we're back. What did you put for the first one? Okay, the first one should be a 4 because you have 4 digits here. Okay, so we have 4 non-zero numbers, so that answer is 4. The next one, did you put 5? Good job. You have zeros with a decimal value in it, and so that 0 being there, or the decimal being there, is deliberately telling you that, hey, all 5 of these digits are being measured. Okay, we have a 0 here, but there's no decimal, so that makes this digit not measurable accurately. So this one is an area, like a square meters here, measuring an area. Perhaps you've measured an area, but it's, give or take 250, or maybe it's 248 or 253. You're not sure, but you only know for sure the hundreds place and the tens place. And then this number, did you put 3? Way to go. Since you're already measuring the first and last columns, then the middle tens place must be measured. All right, so now let's talk about multiplying and dividing these digits and still keeping within the values. What we're doing is we don't want to add to the values, we don't want to take away from the values, we want to stay true to the measured values. So in order to do that, when you start doing calculations, you have to follow a couple simple rules. So one of the rules is for multiplication and division. They're the same. So first you work out the problem, either multiply or divide. And once you do that, you need to reduce your number to the least number of significant figures from the original numbers in the problem. So notice I've underlined, and this one has how many figures? 2. This one has 5 significant figures. So 2 being the least number of sig figs is what I'm going to round the answer, the number in the answer to. Again, this is just the power, the magnitude of the value. It's pretty big. We can't take that part and change it. We just simply leave that alone. All right, I told you there were 2 rules for calculations of sig figs. So what you do here is, if you are in fact adding or dividing 2 numbers, adding or subtracting 2 numbers, you have to line them up by column. This isn't very well lined up, but as you can see, there was that attempt. So add the 2 numbers up. Once you add the 2 numbers up, notice if you look at the columns that this first number ends in the hundredths place, and so since it goes no further, you can't really assume that you can read another digit beyond that for the whole problem. So if you're adding these 2 numbers together, you're going to have to round this answer to the hundredths place, which is right here. Since this number after it is below 5, okay, this number here is below 5, then you can round down. In other words, we can get rid of these last 2 digits. All right, it's your turn again. Solve these numbers, solve these problems, and we'll talk about it in class. right? This one, when you line it all up, you should take your 14.3505, add it to 2.65, and you should get 17.005. However, since this number ends in the hundredths column right here, then we should round this entire answer down to the nearest hundredths place. So if we round this, this will round down to 17.00. Let's go to the next one. This next one is 811. .96. Oops. Let's see here. I'll start it over. One second. Alright, so this next one is 812.0. I need 4 significant figures, so I've had to round the answer up to 812. My next one, just to help you along here, you should have 3 sig figs in your final answer, because this first one has 3 and the second one has 4. So your final answer has to go with the number of least significant digits in the problem. So 3.29 times 10 to the 4th . So we have 8,228, but we need to go with 3 significant figures, so we'll have to round that down to 8,230. So this is a case where if you're going to have to round, you'll have to round up just so that your last digit is a 0 and is now not significant. The last one, oops. Alright, so let's evaluate the number here. We have, starting from the left, you don't count those zeros on the left, so you have 3 significant digits here. And same thing here. So our final answer will have 3 significant digits, so we'll put 0.0869. There you go. Alright, that's it for this page here. Right, I will refer from time to time to the power line. The power line is a neat way to look at exponents, and it gives you a visual of thinking about our most common units. So the base unit is at the 10 to the 0 line, and it doesn't have to be for a gram. It could be for a liter or some other unit, a mole, whatever. But as soon as you put the prefix kilo in front, you've multiplied that base unit by 1,000. So kilo really represents times 1,000. And then if you want to take 1,000th of that gram, if you want to make that 1 over 1,000, that's going to be 10 to the negative 3. It's another way of saying milli, or 10 to the negative 3, 1,000ths. So the reason for the line is that every time you move down one of these rungs, you're actually cutting your sample down by 1/10. So, in other words, if I take a kilogram of chocolate and I cut it into 10 parts, I will have this amount of chocolate. And then if I cut that in 10 parts, I'll have an even smaller part, and I'll have this much, 10 grams of 10 gram samples. And then if I take the 10 gram sample and break it into 10 parts, I'll have 10 1 gram samples of, yep, I was talking about chocolate. And this just continues on. So this one is 1/10 of a gram and 100th of a gram, and finally 1,000th of a gram, or a milligram. Hope that helps. Now we are able to use these to help us make conversions, when we need them. So chemists have a way of setting up their problems to convert from quantities of one unit to another. So for example, in this problem, 687 milligrams is converted into kilograms by multiplying the 687 by the equivalent between milligrams and kilograms. Looking at the number line, you have to climb 6 rungs to get from milli to kilo. Another way of looking at that is saying, all right, a kilogram is equal to 10 to the 6 milligrams. So what we can then do is set this up. So this is what the original question is, what you have originally. This you want to convert to kilograms, which is over here on the far right. So we need to multiply by the conversion factor. We call this the conversion box, or the factor, that allows us to cancel out of milligrams and into kilograms. As long as these two numbers are equal in actual amount, you can plug it into this spot. Again, that's called the conversion factor. Okay, and then lastly, you can take this number and convert it into a form where the decimal's are right behind the first non-zero digit. Okay, let's see if you can make these conversions. You may have to look up some of this on the internet today, so we'll give you a little time here. Alright, for the first one, you have 100 pounds, and you multiply by, let's see, we have 1 kilogram is equal to 2.2 pounds. So 100 divided by 2.2 is 45.3 kilograms. So that's the first one. The second one, you have 100 grams of carbon, and so then you multiply it by 1 mole over 12 grams of carbon. That ends you up with 8.3 moles of carbon. Okay. Number 3. So exchange rate today, I don't know what it is on a different day, but for today, during this recording, it's $1.09 Canadian per dollar US. So, the way I keep track of what I put on top and what I put on the bottom is the given original unit for the conversion step must always cancel with the value, the equivalent that you put on the bottom here. So this is clearly $109. You would get more Canadian dollars. This last one, if you had 100 mils of water and you want to know how many tablespoons there would be, when I looked this up online, I got that there were 0.0676 tablespoons per mil. Oops. And so you would have 6.76 tablespoons. Alrighty. Density, when you think of density, and we spent a lot of time in Chemistry 1 talking about this, lots of empty space, few particles, distance is great between them. So that's picture 1. Second one here, liquid water. You see the water all packed. Not too tight, but they're packed. Look at the solid water here. It looks very orderly. There are some larger spaces than we see in liquid water. Well, the reason why these are different densities is because of their structural makeup. So I point to the structural makeup first so that you can really focus on that for a deeper understanding of density. So why does gas float around in the air? Why does water stay below the floating chunks of ice here? Can you explain that? So hopefully you understand that it is a density difference, and that in fact the ice floats above the liquid water because it literally weighs less per equal volumes amounts. So hopefully a visual that'll help you understand the concept a little better. It's always a ratio of mass over volume. Here's a density problem that you all could probably do. This may take a little bit of thought, so get with your partners or take a moment on your own to think through the problem. You may have to think back to what you did in Chemistry 1. This does take a little review. Pause the screen, and when you're ready for checking your answer, come back. We do this. First of all, what formulas do we need? Well, let's see. Density. Density is mass over volume. That's nice. Now, we're solving for volume. So we're going to have to rearrange the equation. What we can do is write volume. Since d over 1 equals mass over volume, then volume times density equals mass, dividing both sides. We want volume alone, get rid of density. So volume is mass over density. Okay? Alright, so volume is mass over density. So this is what we know from the left side here. Okay, what's the mass? Well, you have 5 moles of aluminum, but you don't know the mass. So let's see, 5 moles. Do you know the mass of 1 mole of aluminum? That's right, it's 27. So we can put that in. Let's see here. Let's fix that. It's a little hard to see. Okay. So mass on top here would be 5 moles times 27 grams per mole. And then the density on the bottom would be 2.7 grams per mil. Now what does happen, and let me use a different pen for emphasis. Well, I can just show you. These 2 moles cancel, and these 2 grams cancel. So what's your answer down here? After you simplify it, it will be in milliliters. Let's just calculate that out to see what we get. Well, here I'm going to start teaching you a lot about doing more mental math. You don't have a whole lot of time on the AP test, and if there are shortcuts to be found, we need to be aware of them. So 2.7 goes into 27 exactly 10 times. So it's 10 times 5, or 50. Let's see if I can get my pen there. Yep. So 50 mils is the answer. Okay. So you can calculate an approximate dimension of this based on its physical property of density.